Okay, welcome back to the course 154 physics. So we would like to we're gonna continue from the last lectures. So last time we were talking about the basic of the concept of the special relativities, and that brings us to the what we call the Rawlings transformations. Okay, so today we're gonna continue. Let's say it's consequences from the special theory of relativity, but basically it's a consequences of the Rawlings transformations. Okay, so last time when we get the Rawlings transformation, we also get that the interpretation between two events also follow the Rawlings transformations. Okay, so not only the coordinates and time, but also the difference between coordinate and difference between times also follow the Rawlings transformations. Okay, so let's start from the first consequences of the Rawlings transformation. It's simultaneous and the relativity of times. Okay, so if we start from the Rawlings transformation of the period of time, the delta t equal to the Rawlings factors delta t minus v ux over c square, where the Rawlings factor is 1 over square root of 1 minus v square over c square. Okay, so what happened? So if we set delta t equal to 0, okay, if we set delta t equal to 0, delta t prime is not needed, right? To be 0, right? As the sorry, I think I put it wrong here. The v, oops. V delta x over c square, right? So as the delta x, it's not 0. Okay, so what does it mean? It means that the event that you see that it's happened in the same time in one frame may not need to happen in the same time if we're looking from the different frames. Okay. For examples, this is the example provided in the survey. So you have the lightning going at the head and the tail of a bogie of the trains. Okay, and then when the lightning comes, it's marked, and then this mark create the light. Okay, to the observer, and then there is an observer in the middle of the train, exactly middles. Okay, so if you're looking from the people who are at rest, okay, so not with the train but stay on Earth. So we start from here, right? So the signal from A and the signal from B, which happen at the same times, create the light, and so the light is traveling with the same distance, so it can reach point O in the same time. So in this case, you say, yeah, that's mean the delta t equal to 0. Okay, but for the people from the person who is on the train, okay, so when the lightning come, it create the signal. So the signal come right from A and B. But since the train is moving, okay, so the observer, it's reaching, it's going in the opposite way as the lightning from B. So it's mean that it can meet it, the signal will reach the observer before. Okay, while he is moving away from the point A, so it's mean that the signal need to go further before it reach the observer. Okay, so in this case, the delta t prime it's not 0. Okay, so this is the meaning or the concept of the simultaneities. So everything that happened in the same time in one frame, it doesn't need to be happen in the same time if you're looking in another frame, except the delta x also equal to 0. Okay, which means the event happened at the same place and same time. Whatever which frame ever you're looking for, it's gonna be happen in the same place and the same times also. For example, you say you grab your hands. So at the moment that this hand touch this hand in this frame, if you're looking from whatever the frame, you're gonna see exactly the same. That's two hands touch each other. Okay. Or for example, or another example is like twin bond. So they're born in the same place and in the same time. So if you're looking from the rocket, you're looking from the plane, you're looking from the train, wherever, you're gonna see twin bond in the same place and the same times. Okay, so this is the concept of the simultaneities. Okay. I hope that you follow. So next it's about the time dilations. Okay. Again, we're gonna start from the Lorentz transformation of the time. The delta t prime equal to delta Lorentz factor, the delta t minus v delta x over c square. Okay. So the delta t tell you how long of the one tick of the time in this case. Okay. Let's take the note first and then we discuss. So the delta t of the clock. Okay. So if delta t it's long delta t, its mean times run slower. If it's short delta t, okay. So the delta t is the period that if you're talking about the mechanical clock, so it's period from the ticks that moving from beginning to the next one. Okay, so this is one tick, it's delta t. So it's mean that if it's delta t is long, so it's move slowly before it reach the next tick, so the time runs slow. Okay, but if it's move fast, the time runs fast. However, to imagine about the time, the clock in the relativity, it's gonna be difficult if you're thinking about the mechanical clock or the electronic clocks. Okay, so what we're gonna use to represent this is the light clock. However, remember that since you are in the same reference frames, so it's mean that the clock need to run exactly the same. Okay, so you use the light clock to measure the second. It should be equal to the mechanical clock. It should be equal to the watch, the electronic one. Okay, because the time should not be different in the same frames. Okay, the clock in that frame should be also, exactly the same. Okay, in the same frames. So so we use the mechanical clock. So, we use the light clock. So the basic of the light clock is that you send the light signal out from one side. Okay, it's go up to reach the mirrors, and then it's reflect back. Okay, and you have the detector also in the same place. So this is the light clock. So this is one tick for the light clock, and you can say that this is whatever fraction of the second. Okay, so if it go fast, the time run fast. If it goes slow, it's the time runs slow. Okay, and it's constant in the frame in the same frame, because it uses the light, so the light traveling at the same speed everywhere, right? Okay, so this is the postulate from the special relativities. So in the I call this is the S frame, this is the S prime. Okay, so for the S frame, you're gonna say that the light is moving and go back to the same place. So basically the delta x equal to 0. Okay, when delta x equal to 0, what you get is delta t prime equal to the gamma delta t. Okay, so this is what you will get. Okay. And you can see that the factor gamma, okay, it's 1 over the square root 1 minus v square over c square. It's larger than 1, right? It's go to infinite when c reach the infinite. So when we reach c, the gamma reach the infinite. Okay, so it's increasing function. So what does it mean? So it's mean that the delta t prime it's larger than the delta t. Okay, so when the delta t prime is larger, so that it's mean the time run slower. Okay, so why it's happening that way? Because if you're looking on the clock, which is addressed with the observer address, and then you are moving. So when you are moving, you're looking to that clock. Okay, you are in S frame, but you're looking the clock in S. Okay, look at the clock in rest. Okay, so you're gonna see that the light is not traveling at a straight line, go up and down. It's traveling as a straight line, but it's not in the shortest directions, shortest distance. Okay, because you see that the clock is moved, right? So when the clock is moved, the distance is increasing, so the delta t prime is increasing. Okay. In this case, we call the delta t as the proper time. Okay. The proper time. Be careful when you define the proper time. The proper time is depends on the observer and the clock. Okay, the proper time can happen when observer is with the clock. Okay, observer is with the clock. Like if you are in the rest, you are in the world, you carry the clock. So your friend which is running, they don't have the clock, they're looking on your clock. Okay. Or if your friend is running and he has a clock, so for him, his clock is at rest because it's go with him, right? So you, which is staying at rest from your point of view, but from your friend, you are moving. Okay, so this is can create your confusion. Just to make sure that when you're talking about the proper time, okay, the times in the frame that run it's the shortest, the delta t, or the time run fastest. Okay? We are talking about the clock which is with the observer. Okay, I can give you more clear examples. So before we talking about one people at rest, another one is on the train, he's moving, people on the train is looking on the clock, on your clock that you are still at rest. Okay, but now the situation is different. So your friend have the clock and he is on a train. Okay, when the train move, for him, his clock is stay at rest. Okay, so the light it's go back in the same way. But for now, you as observer looking to that clock. Okay, so if you're looking to that clock, you need to use the inverse Lorentz transformation. So you're talking about the delta t equal to the Lorentz factor delta t prime plus v delta x over c squared. Okay, and delta x prime. So in this situation, the clock is at rest with the people on the train. So the delta x prime equal to 0. So what you get is delta t equal to the Lorentz factor delta t prime. Okay, so this is different than what you get before, right? What you get before is delta t prime equal to the Lorentz factor delta t. So this is the difference. But remember, when we're talking about the proper time, the terms that attach to the Lorentz factors, it needs to be the clock, which is at rest with the observer. Okay. The clock is at rest with the observer. Okay, and this is called the proper times. Okay. So be careful. Don't try to remember the formula. Try to understand the concept of the clock. Okay, which one need to be the proper time? And the proper time need to be the shortest one, or the clock run fastest. Okay. So yeah, this is one concept that people can miss at some point. Okay, when you are trying to do, and this is gonna happen also with the length, okay, which we're gonna see next. Okay, so now you get the concept of the proper times, you get the concept of the simultaneous. So next, we talk about muons. Okay, so muon. So muon is unstable particle with elementary particles that it have a charge equal to the electrons. Okay, and the mass is about 200 times than electrons. Okay, so the muon can be produced from the cosmic ray. Okay, so there's a cosmic ray coming out from the object in the universe, okay, in the space, coming, and then it interact with the air molecules. It's breaking, create the secondary particles, and one of that can also create the muons. Okay. By the way, this year it's 110 years of the cosmic ray discoveries on the 17th of April. Yeah, 17th of April. It's 110 years of cosmic ray discovery. Okay. What is the lifetime of the muons? So after measuring in the laboratories, muon have the lifetime of 2.2 microseconds. Okay, when measured in a rest frame, a reference frame at rest with respect to them. Okay, so it's mean you are talking about the muon and you're talking about the clock that people who stay at rest with the muon is measuring. Okay, so if you assume that muon is moving at a speed very close to the light, assume muon moving with speed v equal to 0.99 c, for examples. So the distance that it can travel, it's what? the distance gonna be VT, right? So 0.99 times 10 to the 8th meter per second, right? Time T, which is 2.2 microseconds, okay? And then you multiply all the numbers. Okay, so it's about 650 meters. Okay, so this is the, if you're looking in this point of view, the muon can travel only 650 meters. Okay. However, if you apply the concept of the relativities, we're gonna get more distance. Okay, why? Because on Earth, we can detect the muon. Okay, so if it happens in the upper atmosphere, so it should not reach the Earth, right? We should not have the muon source above us. However, we can detect that. Okay, one of the example is we use the muon from the cosmic to calibrate our detector. So this is what we call the compact muon solenoid detector. It's 100 meters underground. Okay, and this is the track of the muons. Okay, so it's bending in the magnetic field. So it means that it can travel more than 650 meters. So if you cannot remember the height of the atmosphere, you can, I think you go back to the first course that you use the fluid mechanics to estimate the height of the atmosphere, right? You said P0 equal to 0 and P is equal to the atmospheric pressure on the surface. And then you calculate the H, okay, the height. So how can this happen? Okay, so in this case, if you're looking from our point of view, okay, so the delta T equal to the tolerance factor delta T prime. Okay, so this is the proper time measured by the observer, which is at rest with the muon. Okay, so so use the factor tolerance factor 1 minus 0.99 square, right? C square over C square, so it's cancel, and then 2.2 microseconds. Okay, you're gonna get about 15.6 microseconds. Okay, and that's 15.6 microseconds, so it's about 7 times, right? 7 times of that, so you can say that, yeah, so then the muon can travel more than 4,000 so you time 10 to the 8, so it's 4,600 meters. Okay, so it's 4 kilometers instead of 650 meters. Okay, so that's why it can reach the Earth. Okay, it can reach the surface of the Earth or even go down to the underground. Okay, so this is how it's look like. And then if you say, yeah, but then if you're looking on the muon point of view, I have only 2.2 seconds. Why I can go 4 kilometers? So this can answer in the next sections about the length contractions. Okay, so summaries. From the observer point of view, we see that muon have a longer lifetimes. Okay, because the clock runs slower on our frames. Okay, so it can traveling with the more distance before it start to decay. Okay, but if we're looking on the muon point of view, so what happened to us? I mean, why we can travel more than 600? Okay, that's because we see the length is contract. Okay, so instead of we see the length of 4.7 kilometer, it's contract down to 600 meters only. So what we're traveling 600, but it's 600 from the muon point of view. Okay, but that's equivalent to the 4 point something on the observer point of view. Okay, so this is another consequences of the special theory of relativity, which we call the length contractions. But before we go to the detail, which I think you can just write the formula. One concept that you should get is that when you measure the length, it means you measure the head and the tail, this head and the tail exactly the same times on your frames. Do you get it? What I mean? So for example, this is the one pencil, right? Yeah, this may be. So now the pen is at rest with respect to me. So I measure the head and the tail. So I can measure at any time, right? Because it at rest. But now if you imagine the pen move like this, you measure the tail where it is, right? But if you allow it to move and you measure the head, okay, maybe start from here. So you measure the tail and then you allow it to move and then you measure the head. The size is not exactly the same, right? Because you allow it to move. Okay, so what you have to do is that when it moves, in a snapshot of time, you measure it. In a snapshot of time, you measure it. Okay, so you need to measure head and tail exactly the same times. Okay. You measure heads and tail at the same time. Okay, so again, in the same way as the length, the time dilations. So we consider the object in two frames and we're looking from the different point of view, just to make sure that you understand how to use the formula clearly. Okay, so the first is that you know the length in S-plane. So you know the length of the pen which is moving because you are moving with the pen. You know the length, right? Because for you, if you're moving with the pen is at rest with you, you can measure the length all the time. So this we call the L0. Okay. So what we get is we use the Lorentz transformation, the delta x prime, okay, equal to the gamma, the delta x minus right? Yeah. V delta t. Okay. So you measure from the S frame. Measure from the S frame. So you require delta t equal to 0. Okay, you don't need to require the delta t prime equal to 0 because you can measure at any time if you are at rest with the pen, right? But if you measure from the S when you see the pen move, the ruler move, you need to set exactly the times. Okay, so delta t equals to 0. Delta x prime is the length in the S prime frame, so you know that this is L0. Okay, so what you can measure is delta x, which is L. So what you get is L equal to the L0 over gamma. Okay, so L0 is the length which is address with respect to observer. Okay, and it's gonna be the longest one, right? Because the factor gamma is always greater than 1, so the reciprocal is always less than 1. Okay, so this is the reciprocal of the gamma, so which is less than 1. So it's inverse of the gamma. So L is always shorter. Okay. So now we looking on the opposite situations. So the ruler is fixed address in S frame, and you are at the moving frames. Okay. So what you can do is basically you use the inverse of we can use the inverse of this one, which is okay. You can use it almost immediately. But I will show you that if you use exactly the same transformations, how can you do that? Okay, because basically you can use whatever you prefer, right? If you understand me, so if you can use just the delta x equal to the gamma delta x prime plus v delta t prime, right? And then you measure it's 0, so you will get this is L0, so you get L equal to the L0 over gamma. Okay, if you use the inverse Laurent transformations. But if you use the same formula, what will happen? You use the delta x equal to the delta x prime equal to the gamma delta x minus v delta t, and then you have the delta t prime equal to the gamma delta t minus v delta x over c squared. Okay, so if you use this case, you measure from the S prime, so the requirement is delta t prime equal to 0. Okay, you need to set this one equal to 0, which is mean you're gonna get delta t equal to v delta x over c squared. Okay, put the delta t back here. Okay, and then arrange the formula. So the delta x measure as the L, it's gamma L0, right? Minus v square over c square delta x is L0. Okay, so you get gamma L0 1 minus v square over c square. So this term, it's basically 1 over gamma square. So you will get L0 over gamma. Okay, so it's exactly the same formula we are talking. Okay, and the L0, we call it the proper length. Okay, so this is 3 consequences that are very famous consequences from the spatial theory of the relativities: simultaneous, time dilations, and length contraction. Okay, so now you see that if you have the distance of, for example, 4 kilometers, right? Which is the distance that you know at rest of the Earth. So from the example we have before, so if this one is 4 kilometers, So the muon will looking at this distance, but it said no, it's not 4 kilometers, it's only 600 meters. Okay, if this guy is muon. Okay. Sorry, I start to write Thai at some point. Okay. So when the muon look at this, it say no, it's not 4 kilometers. Oh, it's 600 meters. Okay. So this is how the muon think in his frame. Okay, that the distance that he need to travel is shorter than that. Okay. So next it's about the Doppler shift, the Doppler effect. Okay. So what is the Doppler effect, right? If you remember, this is the discuss in the physics one. So you have the observer and the source, okay, and then one or both of them are moving. Okay. This Doppler effect can also happen to the light. Okay. You can imagine the concept that if the source is moving and the observer is moving reach the to the source, okay, you're gonna get the wavefronts quicker, right? When you get the wavefront quicker, it means you get the higher frequencies. But if the source is moving away from you, or you run away from the source, or both of you are going away from each other, the wavefront that you're gonna get, it's gonna be longer. Okay, so you have less frequency of the wave you can detect. Okay, and that's reflect in this formula. Okay, however, the formula need to be reviewed because the light is different, because the light is traveling on the space. Okay, so they don't have the speed of the mediums. So how can we consider the relativistic Doppler shift of light? This is what we're gonna discuss about that. But the situation is the same. You have the stars, you have the source of radiations, the source of the light emission. So it's shining. Okay. So from its point of view, it's at rest. So it creates the wavelength. It creates the wave, electromagnetic wave. Okay, with the wavelength lambda all the times. Okay. But if you are moving to it, okay, so you have the stars and you are on Earth and Earth is moving to it, you get more frequent wavefront. So you can expect that the wavelength that you can detect is the higher than what the star produce. Okay. To analyze that, we are looking on a different point of view. So we are looking as the observer at rest. Okay. So this observer is at rest in S prime. The star is moving. Okay. So first that the star is moving starting from point 1. Okay. So at point 1, the star inject the first wavefront. Okay. Inject the first wavefront. Okay. So the wavefront is traveling with the speed c. So it's traveling with the ct prime if the time pass, if the t prime pass. Okay, this is measured from the s prime frame. Okay. Also, the source is moving, so it's moving with the speed v. So it means that at time vt prime, it's going to the second place, this point, and then it starts to inject the second wavefronts. Inject the second wavefront. Okay. So the period of the t is the period, right? It's the length, the time difference between two wavefronts. Okay. So you have 1 over t prime, it's equal to f prime, right? Or 1 over t is equal to f. Okay. So the difference, next is that the difference between the two wavefronts, it's called the lambda prime. Okay. So from the S prime point of view, the lambda prime, it's equal to the Ct prime minus Vt prime, right? And then if you use V prime equal to the F prime, the lambda prime, but V prime is C, right? So basically lambda is C over F, right? So you can get F prime equal to the C over lambda prime. So C minus V T prime. Okay. Okay. So now we need to change it to the relation between frequency. Okay. So we can use the time dilations to manage this term. Okay. So the T prime is measured from the observer point of view. Okay. T prime, this is from observer S prime point of view. Okay. So it's gonna equal to the gamma T, right? The Lorentz factor times T. Remember, you have the times on the different frames equal to the Lorentz factors, the time as the rest frame. Okay. So this is the time as the rest frame. Okay, so this is a proper time. So this is that. And then what you get is that 1 over t is f. So finally what you get is f prime equal to the c minus v gamma f. Okay. And then if you would like to manage the formula a bit, right? You how can we do that? It's 1 over c, right? Okay, so f prime 1 over gamma is the square root of 1 minus v square over c square, right? Because this is 1 over factors. So it's move up. Move c down, so you get 1 minus b over c, right? Yep. And then you get f. Okay. So what you have is f prime equal to the square root of 1 minus v over c, 1 minus plus v over c, f divided by 1 minus v over c. Okay, so finally you will get square root of 1 plus v over c over v minus v over c times f. Okay, so this is the relationship between frequency that you can observe with respect to frequency that the source emitted. Okay, and remember that in this case we say that v is the velocity that the source approach you. Okay, so if you're saying the source is go away from you, you're gonna take minus v. Okay, so in this case it means that if we approach you, right, So you're gonna have 1 plus v over c is greater, right? And then 1 minus c is less. So it's mean that you're gonna get f prime larger than f. So it's increasing, right? It's higher frequency. Okay. So if the source approach you, okay, you're gonna get f prime larger than f. Okay. If the source go away from you, you're gonna get f prime less than f. Okay. So it's mean that you get smaller frequency or longer wavelength. Okay. Or longer wavelength. Okay. But if it approach you, you get higher frequency, so you get shorter wavelength. Okay, I hope that you can follow. So this is in the summary. Okay, so in the same way as the Doppler effect that you have learned before. So if the source is moving to you, you get higher frequency, shorter wavelength. Okay, this is what we call the blue shift. But if the source is moving away from you, like a moving galaxy away from the Earth, you get less frequency, so longer wavelength. So that's what we call the phase shift. Okay. Just to note that this is what we call the longitudinal Doppler shift. Okay, this is what we call the longitudinal Doppler shift. Okay, there is a situation that what we call the transverse. Okay, that the source is moving not directly approach you, but perpendicular to you. Like for example, you have the observer here. Okay, the source moving like this. Okay, so there is transfer Doppler shift. We will not discuss in this class. Okay, but basically use the same principle on how to calculate. So if you are interested in this, then you can search on this keyword, the transfer, the Doppler shift. Okay. In summaries, with the consequences of the spatial spatial theory of the relativities. So what you have learned is first, it's simultaneous. Simultaneous, right? If delta t equal to 0, delta t prime not equal to 0. Event that happen in the same time in one frame doesn't need to be exactly the same in the different frames. Okay, you have the time dilation. Okay, you have the delta t prime equal to the gamma delta t. Okay, and the delta t is called the proper time. Okay, the proper time is the clock is at rest with the observer. Okay, and you have the length contraction. Okay, so with the length contraction, you have the L equal to the L0 over Lorentz factors. The L0 called the proper length. So the object is at rest with respect to observer. Okay, so this is the concept of the special theory of relativities. However, there is a problem that if you're looking with the relativities, you're gonna see paradoxes. So something that contradict from each other. Okay, that I will give you 2 examples. Okay, but just to remember, whatever paradoxes we are talking, it's not true paradoxes. Okay, because the truth is, I mean, there is only one truth, right? For example, if you measure something and then another people say that, yeah, with the special relativity he can measure the different things, but however, if any analysis show the conflict, right? For example, if you measure the age and the next one, the twin paradox, you say you should, if you have the twin, one twin is traveling and when come back, which one is older? So calculate from the different point of view can show that maybe the one on Earth is older, the one on the spacecraft is older. But when the two meet, there is only one real. One need to be older, right? It cannot possible that when the two meet, one still say you are older than me. No, it's not possible, right? There need to be only one who is older. So it's mean when you have the paradoxes, you need to think about how to use the special theory of relativities carefully. Okay, what give you and what's happened exactly happened in the situations. Go back and think about that. Okay, so this is how to use the special theory of relativity. So you can always see the paradoxes, but when you see paradoxes, you need to think which one is wrong and why it's wrong and how to fix it. Okay, when you fix it, nothing gonna be there will not be any paradoxes at all. Okay? So this is what we call just apparent paradoxes. So it only seems to be paradox, okay, but it's not. It seems to be contradict, but it's not. Okay. So example, if the first one is twin paradox. So there, we will not do any calculation here. Okay. Just introduce you the situation. So the situation is that you have the two identical twins, okay, and one flying to the space with the aircraft, okay, and then he come back, right? So if you use the concept of the time dilations, so people on Earth, right? People on Earth will say, so you're gonna use the delta t prime equal to the gamma delta t, right? So this is the time on Earth, right? So people on Earth gonna say that his time it's run fastest, right? So it's the time run fast because delta t is short, okay? So people on Earth gonna say the people who are on the rocket should be younger from his point of view, okay? But if you are people on the rocket, he will say the delta t equal to the Lorentz factor delta t prime. He carried the clock with him, right? He gonna say, yes, but my clock, it's run, the delta t is smallest, so his clock run fast. So when his clock run fast, people on Earth should run slow, right? Because he said that he at rest and people on Earth is moving. Okay. So this is what we call the paradoxes. So who is older? Okay. So you now see the paradoxes, and now you see that it's not possible that both are true, right? Because when they meet, one gonna know who is oldest. Okay. So in these situations, there is, I think, basically two two explanation. So the first is that people on the rocket, they are not in the initial frame at all, right? They first start have the acceleration of the rockets, and then when they reach the maybe the next the stars Alpha Centauri, like 3 light year from Earth, they're gonna slow, and then they start to turn and then come back to Earth. Okay, so they are not in the initial rest frame. So that's why the special relativity of his clock should not be used. Okay, so he should use the clock of the people on Earth because it's at rest and it's always in the initial frames. Another explanation is that we don't really need to talk about the accelerations. Okay, we can use just special theory of the relativities, but treat it carefully because people on the rocket use 2 frames. He doesn't use only 1 single frames. Okay, first he move out, he go, and then second one he go back. Okay, so people on Earth it at rest all the time, but people on the rocket, so first he move and then he move back. Okay, so he used 2 frames instead of 1. Okay, so this is why the calculation need to be treated carefully. Okay, and there is explanation on how to calculate this one, okay, which is basically simple for the special theory of the relativities. Okay, so this is something that it's written on the book, so you should try to read and understand. Okay, another paradox, what we call the lattice paradox or the barn pole paradox. Okay, so Mr. Gon would like to carry the ladders and pass to the barn. Okay, so you have the barn. Okay, the barn have the windows like this, right? So Mr. Gon would like to carry the ladders. Okay, but the ladder is it's taller than the barn, the width of the barn. Okay, and these windows both door closed for a brief time, okay, to demonstrate that the ladder fits. So it's open and closed in the same times. Okay, so the question is that is it possible that he can move the ladder past to this barn without breaking the doors? Okay, so his friend Kiro said that yes, you can do it with the special relativities. What you should do is run fast, approach to the speed of light. Okay, so from Kiro point of view, so you have the barn. This is his view. Okay, his view. And when Gon run fast, okay, the ladder ran fast, it can fit because of the length contraction. Right? From Kiro point of view, the length, the ladders that Gon carry gonna be shorter because of the length contractions. Okay. But from Gon point of view, say no, we cannot do that because from his point of view, ladder it still be the same length. Okay, but the barn is shorter. Okay, from Gon point of view. Okay, he said no, we cannot pass it because the ladder is still the same length, but your band here, your band is shorter because of the length contractions. So there's a length contraction by the band, at the band. Okay. So yeah, this is called paradoxes. Okay. So what is the problem? What we should think about in these situations? How can we out from these paradoxes? There's a keyword. Keyword is that the both door close for a brief time. It's closed at the same time, but it's the same times of key rule point of view. Okay, so the door closed for the brief of time in key rule point of view. In this view. But two doors have the different positions, right? So the delta x, it's not 0. Okay, so which means that the delta t prime, so when delta x is not 0, it means that the delta t prime doesn't need to be 0. It means from Gon point of view, the door doesn't need to close at the same time. It's closed at different times. Okay, this is time simultaneous. Okay, so if you consider this, there is no paradoxes at all. The ladder can pass. Okay, from whatever point of view, from the Kiro point of view, it can pass because of the link contraction of the ladders. From Gon point of view, it can pass because of the time simultaneous. The door will not open in the same times. Okay, so this is the situation of the Gon and Kiro. Okay, so this is from Kiro point of view, and this is from Gon point of view. Okay, so you can see that from his point of view, the door doesn't need to be shut at the same times. Okay, so no paradoxes. Okay. Okay, so next we are talking about the space times. Okay, what we are talking about the space time is that okay, we start again from the Lorentz transformations, and we try to connect between two events. Okay, for example, the event one, okay, the first event, you do the exam, and then event 2, the second event, you get the grades, right? So event 2 needs to happen after event 1, right? You should get the grade after you do the exam. But if you go back to the Lorentz transformation, if you go back to the Lorentz transformation, the delta t prime equal to the gamma delta t minus Vx over c square. Okay. What you're gonna see is that if you set the delta t, if you set the delta t larger than 0, okay, you set the delta t, which is t2 minus t1, is larger than 0, Okay, the delta t prime does not need to be larger than 0. It's not. There are nothing constraint on that. You just say that delta t prime equal larger than 0. But the delta the delta t is larger than 0. The delta t prime does not need to be larger than 0. Okay. So what does it mean if the delta t prime less than 0? What does it mean? It means that the observer will see event number 2 before event 1. So from your frames, you do the exam and you get the grade. But from one of the frame, whatever, it's possible to find the observer that see you get the grade before you do the exam. And that doesn't make sense, right? Because the event 2 is consequence of the event 1. But the Rowland transformation allow that to happen. Okay. So we can analyze this and see what exactly happened. I think I did something wrong. I used a delta, right? So it should be delta x here. Sorry. Okay. So what's gonna happen? So we discuss about delta t prime less than 0. So if delta t prime less than 0, it means delta t, right? It's less than v delta x over c squared. So v delta, I should maybe use the red one. V delta x over c squared, it's larger than delta t. Okay. Or we can say v over c it's larger than c delta t over the delta x. Okay, if we can find the situation that c delta t is less than the delta x, if we can find the situation that c delta t is less than delta x, you're gonna see the inverse of the events. Okay. Why? Because this one need to be less than 1, right? It's forced by the special theory of relativity that v should be less than c. Okay, this is postulate, so we cannot change it. But the time and the space is not. It's not postulate on that. So it's possible. Okay, so if we find the frame that c delta t is less than delta x, that frame's event 2 will happen before event 1. Okay, so this is the concept. So what does it mean that event 2 happen event 1 if we find c delta t is less than delta x? So it's mean if you have two events, I put it here, you have two events separated by the delta x. Okay, this is event number 1, this is event number 2. Okay, so in the regular frame, our frames, when event 1 happen, when it's happened, it creates the light. Okay, so if c delta t is less than delta x, it means when the time pass and the second event happens, the light from the first event cannot reach the second one. Okay, so this is what we call the c delta t is less than delta x. Okay, but if you have the event 1 and the event 2, when the first event happens, it creates the light. It can reach the event 2 before the event 2 start. So this is what we call the c delta t. It's larger than the delta x. Okay. So if c delta t is less than the delta x, this condition can be true. So there is an observer that can see event 2 happen before the event 1. But if the c delta t is larger than the delta x, c delta t is larger than the delta x, so it's not possible to, if c delta t is larger than the delta x, this is larger than 1, so it's not possible to find v, right? It's not possible to find v larger than c. So it means that it's not possible to see the inverse of the event. Okay, so this is the concept of this thing. So we can make it as a diagram. So you have the x here, and you have the ct here. Okay. So you're talking about the event. So there is a line of x equal to ct. Okay, and this is the opposite, just x minus xct. Okay. So you have the event 1 here. This is the event that have the coexist. Okay, so you talk about the event 1 here. So if you have the event 2 here, okay, so what is the delta x? It's here, right? The delta x is here. The delta c delta t is here. Okay, so in this case, c delta t is larger than the delta x. Okay, so it's mean that this event, the event 2 need to happen after event 1. Okay, it doesn't need to be consequence of level of the event 1. It just need to happen after the event 1. Okay, for example, the event 1 is that I have the breakfast. Okay, event 2 is you have dinner. So you have dinner, it's happened after my breakfast, but it doesn't mean that my breakfast make a consequence that you need to have a dinner, right? It doesn't link. It's my food and it's your food. It's a different time. It just happened that I have the food before you have the dinners. Okay, so this zone, I remember that if I use this color, you not see it. No, I don't see it. If I use okay, I can see that now. So this zone, it's what we call the absolute future. Okay, and this one we call the absolute past. Okay, so the event in the past happened before the present, and the event at the present happened before the futures. Okay, so there's past, present, and future. Okay, so now if you have the event which is here, okay, at here you have the delta x, it's larger than c delta t. So it's mean event here doesn't need to happen after this one. It depends on the frame of the observer. Okay. And if you're talking about the sci-fi thing, so you can say that if this event happen and we somehow know that, we cannot change it. Okay, this event we cannot change, because if we want to change, we need to traveling faster than the speed of light to reach this one, right? Because you are here, but you know, yeah, what's gonna happen here, okay? So if you want to go there and fix, you need to traveling faster than speed of light to reach here, because the light cannot reach it, okay? So you need to travel faster than speed of light to reach this event. You need to move faster than c to reach this event. Okay. So this is something that's what we call the space-times and how to play with the space-times. Okay, hope that you understand the concept of the presents and the futures. Okay. Last topic of today, I would like to discuss about the accelerations in the spatial theory of the relativities. And then you say, no, don't do that, because we are talking about inertial frames. Right? I said, yes, we are talking about the inertial frames. But what I'm talking about is that we both in the inertial frames, one see the object is traveling with the accelerations. So what we can see from the different point of view. Okay, so I'm here looking for this rocket with the accelerations. So you are here. So what you gonna think about that? Okay. So we can do the concept. We can solve this one using the velocity transformations. But before we start that, we starting from something that we know, that the ax prime, it's basically should equal to the ux prime by dt, right? And the ax should be equal to the dux by dt. Okay. So we start from the velocities transformation. Okay. So the velocity transformation is ux prime equal to the ux minus v 1 minus uxv over c square. Okay. So what you should do is that you try to find the ux prime. Okay. So basically it's dux divided by 1 uxv over c square plus ux minus v 1 minus uxv c square to the 2 and right, and then you take the minus 1 and then just a second. Maybe I write it this way, 1 minus ux vc square minus 1. So you get first the minus 1 and then 1 minus uxv over c square to the minus 2. So it's go to the denominators. You differentiate inside, so you get minus v over c square. So the minus cancel. Okay, you arrange the thing. What you should do is basically use this square, and then you multiply this term by 1 minus ux v over c square here. Okay, let's try to do it by yourself. What you're gonna get after you form this, you're gonna get dux. Okay, 1 minus v square over c square divided by 1 minus vux over c square. Okay, you try to manage from this line to this line. Okay, and then you have the dt prime, right? So it's basically from the we can maybe just write it. So t prime equal to the gamma t minus vx over c square. So you find the dt prime, right? Which is the gamma dt minus v dx over c square equal to the gamma dt 1 minus vux over c square, right? You put the dt out, and then dx by dt is ux. Okay, so now you can merge these two equations. So dux prime by dt prime, right, equal to the 1 over gamma dux by dt, which is okay. And then you have the big bracket from here. Okay, and you have the bracket from here. Okay, arrange the term. Okay, let's try to do it by yourself. Okay, so finally you're gonna get, so this term is ax prime. Okay, this term is ax. Okay, this is the how it's look like. I make the final one for you. 1 over gamma to the third. Okay, 1 minus vux over c squared to the power of 3. Okay, so this is the accelerations if you're looking from the difference frame. Okay, and then the same if you want to do the inverse. So you can switch between a prime and a, and v to minus v. Okay, so then you can make the inverse. Okay, so you can make the inverse, so you can ax equal to the ax prime, so whatever divided by 1 plus v, something here. Okay, okay, so this is the second lectures of the spatial theory of the relativity. We're gonna have the last one, okay, which we will focus on the kinematics of the particles. Okay, today it's today lecture it's maybe make you confused. You need to get review of what we discussed in the class. Okay, try to finish the lectures, and then we gonna finish the next one, and then we do the exercise together. So that I think we resolve your any misunderstanding or any confusions. Okay, reading the listening to the lecture only is not enough. Okay, you need to try to do the exercises by yourself. Okay, but at least you need to start from you finish the lecture first. Okay, you start to understand the concept and how to use the formula, and then try to use that with the exercises. Okay. Okay, so thank you very much for these videos, and we see at the next one. Bye bye.